Let's talk a little bit about integration strategy. So I would say the first thing is you really need to memorize the basic antiderivatives. I mean, if you see the integral of secant squared x dx and you don't immediately recognize that that's tangent x plus c, well, I don't know what to tell you. So you really have to know the basics. Now, in this class, we've learned how to integrate a few other basic antiderivatives. So we've also learned how to integrate something like b to the x, right? We learned how to integrate 1 over x dx, obviously. We learned also some new trig derivatives like the antiderivative of secant x dx or the antiderivative of tangent x dx. These are all now considered basic antiderivatives for you. All right. I think in general, these go from like easiest to most difficult. So uh, sometimes simplifying will make your integral a lot easier. And this is what we did in 5a. So let's say you had some integral that looked like, the cube root of x times 1 over the square root of x plus x to the 2/3 power, something like this, dx, right? Well, on the surface, this looks complicated, but if you changed each of these guys to exponential form and then you distributed, this would simplify into something that you could use the power rule on, okay? I would always look for an obvious U substitution. I'm not going to lie, being able to recognize when a U substitution works, that generally takes a lot of practice. You almost have to see the derivative sitting in the numerator. Okay, so that's a 5a method, but it still remains one of our most powerful. Really, in 5b, we work a lot on classifying according to its form. So what do I mean by that? I mean, if you see a whole bunch of trig functions in there, that's like a 7.2 integral, and you may want to change the way it looks. So we would use trig identities to change the way that looks, right? So that's for trig functions. Rational functions, rational functions are polynomial over a polynomial. A lot of times you want to use partial fraction decomposition. I just want to mention, be sure to try U sub first, okay? And because sometimes, you go through this whole trouble of doing the partial fraction decomposition, and U substitution really would have worked all along. Whenever we have radicals, radicals really lend itself to different integration techniques. So it's something like plus or minus x squared plus or minus a squared, and then you have a radical involved. We had 3 different cases where of using trig substitution, right? And a lot of times, this is going to turn your integral into a trig function integral after you make your substitution. If you have something where it's a strange index, so it's not a square root, but it's sort of an nth root, a lot of times we can make a rationalizing substitution. And the way that we do that is, you would let u be equal to the nth root of ax plus b. So if you did that, then that would mean that your u to the n would equal to ax plus b. And then you would differentiate both sides, right? So you'd have a n u to the n minus 1 du would be equal to a dx. And then you could solve for dx, and a lot of times you could also solve for x, right? Your x would be equal to u to the n minus b divided by a. So using one substitution for dx, right? You could solve for dx, and one substitution for x. This might make your integral easier. These last three kind of seem like a joke, but it's really not a joke. A lot of times your intuition is wrong at the beginning. And only the easy integrals fall apart quickly. There's a lot of integrals that are very tricky and you need to try different things. Sometimes I would try something different. So let's say it looks like it's one of these types up here, but it didn't work. Try something even if it doesn't look like it might work. For example, we said, oh, you might want to use trig substitution if there's a radical. Well, in our partial fraction decomposition video, we saw that there was an example where we used trig substitution and there was no radical. So sometimes you have to try something radical. Finally, you might need to mix different methods together. I mean, a lot of times trig substitution devolves into a trig integral. So a lot of times you already mix different methods together. What are some other tricks I would say? Well, I would say you could try to change the way it looks. Change the way it looks by multiplying by 1. You can multiply top and bottom by something, and sometimes that will help you integrate it. For example, let's say you had an integral that looked like this. It's like the integral of 1 over cosine x minus 1 dx, like this. And you're like, there's not a lot of structure. I don't know how to proceed. None of these other integration techniques work. Well, try something different, Maybe multiply top and bottom by the conjugate of this guy. So maybe multiply top and bottom by like cosine x plus 1. This is what I mean by multiplying by 1. When you multiply by cosine x plus 1, divide by cosine x plus 1, that's really just equal to 1, right? But maybe when you do that, then you'll have a difference of 2 squares here, and then you could maybe use some trig identity, and then maybe that would help you unpack this integral a little bit easier. Okay. So, we'll look at more examples in class. Take care, everyone.